Hey guys, hope you've been keeping safe with all the coronavirus stuff. Today I'm planning to go over enolates, so we're going to be going over acid-base properties of our carbonyl groups, what an enolate is, and the different types of them and how we can use them for reactions, and then I have some practice problems at the end. So let's get started. So from our previous video, we know that there's four types of carboxylic acid derivatives. We have our amide, we have our ester, anhydride, and we have our acyl chloride. From the previous video, we've established that as we move right, there's increasing reactivity. The reason why is because all four of these molecules are electrophiles. The most reactive electrophile is the one that has the biggest partial positive charge here. This chlorine does just that. The reason why is because all of these groups donate electron density through resonance, but chlorine has a very large induction, and because of that, it sucks away electrons from this carbonyl center, making this have a very large partial positive charge. Because of this, it's very easy for a nucleophile to come in and just attack this center. So we learned that those are the properties of our derivatives. So now we're interested in acid-base stuff, and let's look at a simple example of an acid base. Let's look at carboxylic acid. This is our carboxylic acid, and then we have our base over here, and it has its lone pairs. So we know that the acidic proton on our carboxylic acid is this guy right here. So our base is sort of going to use its use its lone pair as like a lasso, grab this proton, and it's going to kick off this bond onto the oxygen. So now one important thing to note is that this bond is going to the left. So if I had a bunch of fluorines just on this side of the carboxylic acid, it's nowhere near where this reaction is happening. But we know the fluorines will cause an induction and a dipole this way. It's going to suck electron density here. So it's sort of going to help push this bond over here. And because of that, we know that electron withdrawal increases acidity, because these fluorines are withdrawing electron density, and that sort of helps this single bond pop off onto this oxygen over here. So remember, we're looking for electron withdrawal with our strongest acids. We know that as we move right here, there's more electron withdrawal because it increases the positive charge here. So theoretically, as we move to the right, we should get better acids. And let's see if that actually works in practice. Well, our amide should be the worst acid, and we see that it has a pretty high pKa, so we know it's not that good of an acid, so that makes sense. Then we have our esters next, and then here I put a ketone and an aldehyde, and lastly a beta-dicarbonyl group. So let's quickly go through the understandings of why this is happening. So we know that this nitrogen donates some electron density to the center, and this oxygen does the same thing. But this oxygen is more electronegative. It sucks away more electrons through induction, and because of that, this will be more electron withdrawing. And because of that, we know that electron withdrawal increases acidity. So that's why this guy has a lower pKa than the amide. Here we have a ketone and an aldehyde. We know that, let's go back to Orgo 1 when we had something like this versus something like this. Which one is the better carbocation? We know that it's going to be this guy right here, and the reason why is because it's a tertiary, and these methyl groups are donating electron density through induction. And there's a special word for that called hyperconjugation. So we know here, these guys are the same except for what's over here. Here we have a methyl group, whereas opposed to here we have a hydrogen. From Orgo 1, we learned that the methyl group can donate electron density through hyperconjugation. And electron donation is bad. We want electron withdrawal to be a good acid. So that's why this is a worse acid than the aldehyde. And then here, this is a superb acid. It's 10 magnitudes more acidic than what's up here. The reason why is because if I put a lone pair on this middle carbon over here, it can resonate both to the left and to the right. And we know, like, let's say I take an acid up here, and if I deprotonate the acid, we're going to end up with a base. The more stable the conjugate base, the lower we push this down, the bigger the roller coaster, right? And we know we want to ride that roller coaster more if it's a bigger drop. So Because we can resonate both ways to both carbonyls, we're making a very stable conjugate base. And because of that, we're kind of increasing the drop on a roller coaster, and our acid wants to react more. So this makes it more acidic. The sole reasoning is just because it can resonate to both carbonyl groups. So this is an aldehyde, and usually I ask this to kids in Orgo 1 because this is a very common misconception. I ask them, what's the acidic proton here? We know we have a base, so it's going to have to abstract the proton. Well, they'll say, of course, it's going to be this one because it's just sitting out here in the open. Well, if I abstract this proton, what we're going to get is a lone pair on an sp2 carbon. That's very unstabilizing. It's not a good conjugate base. It's not going to be stable. In fact, we don't use this proton. What we do instead is we grab a proton from the alpha carbon. And in case you guys forgot your Greek lettering, the way it works is, let's just extend this chain just to prove the point. So if we want to use Greek lettering, we don't start off at the carbonyl carbon, we start one over. So this will be your alpha, this one will be your beta, this one will be your, I hope this is a gamma, I don't know the rest of them, alpha, beta, gamma, delta, the rest of it's not important. But on your alpha carbon, you're going to have protons, 2 of them. So your base will come in and abstract one of the protons and kick off this bond. So what you should be left with is this. This hydrogen stays, but now we have a lone pair here. So now, why is this better than this? The reason why is because here your lone pair is unstabilizing. It has a negative charge associated with it. The way we fix this negative charge is we resonate it. Here we can resonate, here we can't, because if I take this lone pair, I can push it up and then we can push this pi bond up. So we should get something like this. Negative charge on the oxygen, and now we have a alkene. So this is basically what an enolate is. When you deprotonate a carbonyl compound at its alpha carbon, so I should write alpha here just so you guys know, at alpha carbon, you get an enolate. So when you deprotonate something at the alpha carbon, you produce an enolate. So these two are just resonance contributors, so we could draw that in. And they are the enolate of this aldehyde we have up here. So now you guys have heard a bunch of similarly sounding words. You've heard of enolates, you've heard of enols, enamines. It just gets very confusing. So I'm going to try and explain what the difference is so we don't get too confused. So let's start off with our aldehyde. We know that if we add a base, we're going to deprotonate it. Screen. So if we add a base, and remember we're going to deprotonate it from the alpha carbon. We don't start numbering it here. We start saying this is your alpha carbon. So we know there's a hydrogen here. There's a hydrogen here. Your base is going to come, grab that hydrogen, and push off this bond onto the alpha carbon. So you should be left with this. That's why your lone pair is now here. But remember, this can resonate, and that's stabilizing because you're stabilizing the conjugate base. So you should be left with this. This is the resonance contributor. And remember, whenever we deprotonate a carbonyl at the alpha carbon, we create an enolate. So now we really have 2 choices when we have an enolate. It can go down 2 different reaction routes. The first one is it can use its lone pair as a nucleophile and attack an electrophile. That's only if an electrophile is present in solution. The other route is if there's nothing left, you just reprotonate and you create an enol. So let's do the first one. Let's say I have some electrophile just floating around in solution. No, it's ugly color. Let's do ethyl bromide. So remember, this is an electrophile. This lone pair is going to come in, attack this, and kick off this bromine. So what we should be left with is this product. So 2 carbons from here, so 1, 2. this should be your product from nucleophilic addition. Now, that means that your enolate is synthetically useful. It can use its lone pair to grab an electrophile. So that's pretty good. But now let's say we don't want to do that route. We want to go the second route, which is creating an enol. We just protonate this oxygen. So let's say it just grabs a proton from solution. So let's just say there's just a proton just, oh god, it's minding its own business over here. It's going to grab it, and what we should be left with is this. And remember, this is called an enol because En for alkene and Ol for alcohol. So if you guys remember from Orgo 1 and however much of Orgo 2 you've had, the enol is not the most stable form it can take. It can tautomerize, and that's just a fancy word of saying it can rearrange into a ketone. So what we could do is, what's a good color? Let's use black. It can tautomerize back to its ketone form up here, or aldehyde form. And it generally prefers to be in the keto form over the enol form. The reason why is because this ketone, or aldehyde in this case, has a carbonyl group. Your carbonyl group is much more stable than this alkene because it's a shorter bond, it's more stable, and it's more polarized. So we prefer to form this. However, that's not always the case. There's one exception to this that comes to mind, and that's with phenol. Our phenol over here is also an enol. It has an alkene, and it has an OH up here. So by that metric, if we use the above principle, we should say, oh, okay, well then it should tautomerize to this. Well, okay, yes, this is a theoretically correct reaction. But what's happening here? We tautomerize, but we're also breaking something very important. We're breaking aromaticity, so this is very unstabilizing. So always make sure you examine the entire reaction. Tautomerization does have some exceptions here or there. So as I said before, your enolate, so we had our aldehyde. We use a strong base to deprotonate it, and we create our enolate right here. Now your enolate, as I said before, it has two options. It can either protonate and form an enol, which then tautomerizes back to your original aldehyde, or it can do nucleophilic addition. So let's just draw the nucleophilic addition in so you guys get an idea once again. Let's just do something more fun this time. Let's use something like this. So if I do that, this guy's going to do nucleophilic addition. And there's 1, 2, 3, and then second to last. So 1, 2, 3, and second to last. So this should be your nucleophilic addition product. That's fine and all. I don't really care about this product too much. The one that's more interesting in this case is our enol. So here, let's just protonate again. Grab that proton that's just sitting around. And what we're going to get is this. So here we form our enol. However, there's something very interesting that just happened here. We know that the enol will tautomerize back to its original carbonyl form. So it's going to go back, it's going to go back to this guy, and it's going to prefer it more than the reverse reaction. Now, here's something interesting. This alpha carbon has a chiral center. So here it's sp3 chiral. When I abstract the proton from the sp3 carbon, it becomes planar. So here this enolate becomes sp2 planar. I've essentially eliminated all stereochemistry from the problem here. So once I create our enol, there's still no stereochem, except for the alkene, but that's not what we're talking about. There's no stereochem at this initial alpha carbon. Nothing going on over here. It's flat because it's on an alkene. This is sp2. So when I tautomerize back here, we're going to regenerate a stereocenter, but it's not going to yield the same product here. Instead, what we're going to get is a mixture. And you guys have heard this word before. You're going to get a racemic mixture, a 50-50% sort of yield. So let's take an example. There's often like a common box problem on this. So let's say I have this aldehyde right here, and then I put it in a strong base, lithium diisopropylamide. That we'll get into that later. That's not the point right now. So we're going to abstract an alpha carbon hydrogen. So we're going to take off this hydrogen, and we're going to form a carbanion. So in reality, you're not going to get just one product. You're going to get two products. Two products. The first one will be the exact same as your product. The second product will be the inversion of it. And if they ask you which one's the major product, it's a trick question because this is a racemic mixture. So in this case, it's going to be a 50-50% split. So this one's going to be 50%, and then this one's going to be 50%. And the reason why we get a mixture of racemic things is because in this enolate state, we essentially eliminate stereochem because we go into an sp2 planar state. So yeah, we use LDA to create the enolate, and then you could just say like add water or H+ to regenerate our enol. But our enol will have like 50% R, 50% S. So in addition to enol and enolate, which we just covered, we also have went over enamine in the past. So all of these end up doing nucleophilic addition reactions. So like, what's the difference? The main difference is actually lies in terms of reactivity. So let's examine what's going on here. So we know all three of these, the enolate, enamine, and enol, are going to act as a nucleophile. So let's put an electrophile in front of it. Different color. I'll just put ethyl bromide again. So we know what's going to happen is that this oxygen is going to push down, and then this pi bond is going to attack and kick off this bromine. In this case, this lone pair is going to push down. This pi bond is going to come in and attack this carbon and kick off this bromine. And in this case, the lone pair and the oxygen is going to come down. This pi bond will attack this carbon and kick off the bromine. So it's a very similar mechanism. And now let's see what the products will look like. So for the enolate, it should look something like this. And because it's two carbons you're adding on, it'd be 1, 2. Something like this. For the enamine, it's not fun to draw. You're going to get a pi bond here, so positive charge on this nitrogen. And then you're going to get another 2 carbons here, so 1, 2. For your enol, once again, you're going to get a pi bond here that you just created, but this H is still remaining. Now that this oxygen has 3 bonds, you need to give a positive formal charge. And you added on 2 carbons, so 1, 2. So let's look at this product. The one that has the most stable product will be the one most likely to react. Because remember, in terms of energetics, we want to have the longest roller coaster ride. We push down our products, make it more stable. This wants to react more. So we know that our enolate is more reactive because it has higher energy, because it forms more stable product. The reason why is these guys have a positive formal charge. This enolate doesn't have that formal charge in its product state. These guys have to do an extra step to eliminate that. And in addition, we know negative charges like to be on electronegative atoms. So negative formal charge on electronegative atoms. positive formal charge on electropositive atoms. We know our nitrogen is more electropositive than oxygen, so the positive charge prefers to be on this nitrogen. So that's why our enamine is slightly more reactive than our enol. So this is just like ranking the differences. So now we need to go into an important concept, and that's we've learned from, let's go back to what we did in the very beginning. We did the pKa table of these important carbonyl groups, and we learned that aldehydes and ketones are about 17 to 20. So 17 to 20 means it's not that great of an acid, because it's already in a pretty stable state. If I abstract a proton, I'm going to create a charge, and that's not very stabilizing. So I'm essentially going against what our reaction wants. Because of this, I need a very strong base to drive the reaction. So in reality, like I used NaOH, that was incorrect. I was just trying to make a point. You can't use a relatively weak base like NaOH. You want to use something stronger. The ones that we usually use for single carbonyls are, we use either LDA, which is lithium diisopropylamide, or we use NaH, sodium hydride. The reason why is because if you look at LDA, the pKa is about 36, and the pKa for NaH is about 33. So that means that because if it's a high pKa, it's a very weak acid, and because of that, it's a strong base. So we know the strong base is able to compensate for this. So let's give this a try. Let's put our lithium diisopropylamide in there. So amide means we're starting with a nitrogen, diisopropyl, so we're going to get groups like this flanking it on both sides. And we know there's a lithium, so there's a positive charge in here somewhere. The lithium is there to counteract a negative charge, so the negative charge is on the nitrogen. So these guys complex together. So this is like an ionic interaction right now. So because of this, it has a negative charge, it's going to act as a very good base. And then what's going to happen is it's going to grab this proton that's just sticking off here. So it's going to use its negative charge and just grab this proton and kick off this bond. So what we should be left with is this. This is our protonated LDA. So we know that the pKa of this aldehyde we just started with is about 17 to 20. Let's just use 20 for right now. And the pKa of this LDA is about 36. So this is the protonated form, so we know we have to write the pKa for the acidic form of it. So that in order to find the pKa of a reaction, you take the pKa of the acid on the left and the pKa of the acid on the right. So the one on the left, this is your acid because it's donating this proton, and we know it has a pKa of 20. So let's write that in. Here, we know we're forming an acid on the right over here, the conjugate acid of LDA. Has a pKa of 36. So 20 minus 36. What that means is the pKa of our reaction is going to be about negative 16. To get that in terms of K equilibrium, what we have to do is we have to do 10 to the minus pKa of the reaction. Or in this case, we know our pKa is negative 16. So if I put a negative 16 here, the negative signs will cancel out, so you should just get 10 to the 16th. That means that our products will be more prevalent about 10 to the 16th times per every reactant we have. So that means it's good. This reaction will go forward very well. But now, let's say I just used a very bad base, so let's use that example now. For example, let's try and use water and NaOH. So if I use NaOH here, we know that it'll grab this proton, same thing as before, and kick off this bond. We form our conjugate base here, and since our OH grabs a proton, it's going to form water. Well, we know that the peak, let's erase this first. So we know that the pKa of the acid on the left is 20. and the pK of the acid on the right, which is water because the water grabs the proton, is about 16. So if I plug it into this formula, it's going to be 20 minus 16. So you get about 4 for the pK of the reaction. If I plug it into here, we know that the equilibrium constant is going to be 10 to the negative fourth. In other words, there's going to be about 10,000 reactants for every product. This reaction won't go forward, it'll go backwards. So that's why this is this sort of the proof for why we can't use weak bases like NaOH. We have to use strong bases, and the ones we use for this are LDA or NaH. So let's just quickly summarize everything we've done so far. We ranked our derivatives in terms of acidity and basicity. We learned where our bases will grab a proton. It'll grab it from the alpha carbon. We learned that if we take our carbonyl group and we use a base, we're going to create an enolate. The enolate has two options from here. It can either add on to an electrophile and create an addition product, or it can form an enol by just protonating itself. This enol will then tautomerize back to the carbonyl. However, the problem with that is that if we have a stereocenter on the alpha carbon, the stereocenter will be wiped clean when we form the enolate. So we're going to get a racemic mixture. And then here we learned that we have to use a very strong base like LDA or sodium hydride in order to create our enolate. So in the first half of this, we were working with things like aldehyde, where you can only create an enolate from one side. But now I have a ketone. With this ketone, this base can either abstract a proton. Remember, we only abstract alpha carbon protons. We can either abstract this one or this one, and that can yield two different products. These aren't the same thing. So then that makes us decide, how do we choose one of them? And this requires an explanation of thermodynamics versus kinetics. So let's take our initial reactant. We know that we can either deprotonate it from the left side or the right side. So let's first take the left. If I take off this hydrogen on the left, I'm going to form an alkene here. So this is the product we'll get. This is our enolate. If I take off this proton from the right, we'll form the enolate on the right side. So these are two different products. The one on the left is called your thermodynamic product, while the one on the right is called your kinetic product. Your thermodynamic product is more stable. That's why its products is much lower than the kinetic products in terms of energy. The reason why is because this alkene is more substituted. It has 1, 2, 3 alkyl groups. This guy only has 2. And we know that alkyl groups are stabilizing for alkenes because they donate electron density through hyperconjugation. Our kinetic product, on the other hand, it doesn't have as stable of a product because its alkene isn't substituted. Because of this, it's not that great. However, if we look at our activation energies, we know that kinetic product has a much lower one. And we know that the activation energy is your main barrier. So theoretically, even though this guy isn't the best product you can form, it'll form faster. And that's why it's called the kinetic product. Kinetic, you can think of it like kinetic energy from physics. It wants to move fast. And the reason why is because it's easier to get over this transition hump, even though you don't have as much to gain because it's not as low as the thermodynamic. On the other hand, the thermodynamic has a much higher hump to get over for the activation energy. But then once it does, it's at a nice area. So now we understand why your thermodynamic products is lower because the alkene is more stable as compared to your kinetic product. However, how come your thermodynamic transition state is more energy? That seems a bit paradoxical. The way I think of it is it's based on the energetics of your halfway through your reaction. So for example, if I was trying to take this proton off to form the thermodynamic product, it's going to be pretty hard to get in here. The reason why is it has like 2 methyl groups sticking here. Whereas if I was trying to grab this proton, there's only 1 methyl group. If I was a base, I would prefer to grab this one because it's easier to get around. There's less steric hindrance. Because of that, your kinetic has a lower activation energy because it doesn't have to get in there as much. Here it has to really get in the right conformation, and it's harder to, so it requires more energy. So let's just summarize what we've learned so far. Our thermodynamic has lower products because it's a more substituted enolate. That's the most important thing. It's most substituted. Your kinetic, even though it's not as stable, it forms faster. And the reason why is because it's easier to get in that smaller space and grab and abstract that proton. So how do we choose between kinetic and thermodynamic? We understand that these two things exist, but how do I prefer it? I feel like if I was just given it by chance, it's going to form your kinetic most of the time. The reason why is because it just has lower activation energy, and you're right. But how do I favor the thermodynamic one? Well, this is all in terms of energy, the y-axis over here. So if I want to get over this hump, I need to apply energy. The best way to apply energy in a chemical reaction is to use heat. So if we heat up this reaction, and that's why I just put some fire here, it'll be able to get over this hump and reach the products. Even if some kinetic product form, if I add some heat, it'll slowly creep back up and come over here and slowly creep back up again and form a thermodynamic product if I add heat. So heat is how you prefer your thermal product. And one way I remember this is like thermodynamic has the word thermo in it, and thermo thinks of like thermometer and heat. So that's one way you can think of it. So let's look at an example of this. Now you guys understood what we're dealing with. So this is another asymmetrical ketone. We have this alpha carbon and this one. Both of them have protons we can abstract. So how do we decide? So on both of these arrows I have LDA, which is a pretty good base, as we learned from before. So it's going to grab a proton. The thing is it going to grab it from this side, or is it going to grab this proton over here? Well, let's go back up to our graph. We learned that if we want to grab the thermodynamic product, the most substituted alkene, we have to add heat. Here, we know that 25 degrees Celsius is much warmer than -78. This allows it to get over that larger activation energy. So we're going to form the thermodynamic, otherwise known as the most substituted alkene. So we should get this. So here we form the most substituted alkene because there's heat in the system. Over here there's no heat, so we're going to form the kinetic product by default. We know our kinetic product, even though it's not as stable, it'll form faster because it's less activation energy. Alright, cool. So now we have two different enolates. Let's add an electrophile because we know with enolates there's two ways the reaction can proceed. Remember, if we have our enolate, it can either do nucleophilic addition if there's an electrophile present, or it can form an enol if it gets protonated. So here I added an electrophile in both cases because that's just more an interesting reaction. So what we should end up getting is this. So our O- comes down, and then our pi bond is used to attack this and kick off the bromine. So we have two carbons adding on, so it should be 1, 2. Over here, it's a similar line of thought. Our O- is going to come down, and this pi bond is going to come here, attack this electrophile, and kick off the bromine. So these should be your two products. This is going to be your thermodynamic product, and this is going to be your kinetic product. So what we learned today was when you have an enolate, even if there's two sides you have to choose from, you can choose based on the addition of heat, which allows you to be more regioselective. So now we learned enolates with one carbonyl compounds, but you can also do it with two. These are the two most common ones, your acetoacetate or your malonic ester. Last video I went over our beta-dicarboxylic acid compounds, and I taught you the acronym "Oh my, such good apples." And we learned about malonic acid. So this is very similar in structure, except replace the acids with an ester. So now we have a lot of carbonyl groups and a lot of enolates, and now you should be thinking, okay, there's a lot of stuff. What's the benefit? Like, why is this one better now? There are some reasons. The first one is that this is a very strong acid. If you go back to our very first table we made, we learned that our beta-dicarbonyl compounds have a pK of 10, much more acidic than the ones we've been working with prior. So because it's more acidic, it doesn't require as strong of a base. It doesn't need that LDA or NaH. It just needs something mild, something decent enough. So we can just use something like ethoxide, NaOET, which is what we have down here. The other benefit is that we don't have to worry about any of that regioselectivity like we had here. We don't have to worry about, oh, let's create a kinetic versus a thermodynamic. There's no kinetic and thermodynamic for beta-dicarbonyl compounds. It's just the one in the center. How come the carbon in the center is more acidic than, let's say here, how come it's more acidic than this alpha carbon over here? The reason why is because once I create a lone pair here, it can resonate to both the left and to the right. Because of this, it can delocalize its charge over 2 oxygens. Whereas if I put a lone pair here, it can only delocalize that negative charge over 1 oxygen. It's better here, so that's why this proton sticking off in the middle is more acidic. So let's take an example of our acetoacetate, and we add ethoxide in ethanol. Our ethoxide is going to act as a decent base, and we know we're going to abstract the proton in the middle because the carbanion that results from this can resonate to both oxygens. So our base is going to grab this proton and then kick back this bond. So we should get something like this. So it's not too bad. Now let's see some interesting reactions we can use this with. Now let's start with our acetoacetate again. We did our first step already. We created our base. Now we add in this, I don't even know what it's called, but we add basically an electrophile. We created our nucleophile. We have an electrophile, so now we can just attack. So this lone pair is going to come off, attack this carbon, and then kick off this bromine. So what we should get is this. So now we're going to have 1 carbon and then our 6-membered ring. So 1 carbon and then our 6-membered ring. So we should get something like this. Now we have 3 more steps on the same intermediate. The first one is NaOH, a good base, then acid, and then heat. Well, if you guys remember from the last video, this is actually a pattern, and we'll go into it. So if we have base, we know we really can't do any reaction here, but we can hydrolyze this ester. Remember, base catalyzed ester hydrolysis. So that's called saponification. Now, when we hydrolyze our base, we're going to create a COO- or carboxylate anion. So in order to create our carboxylic acid, we need to just add an acid workup. That's what this step is. And then lastly, we're going to decarboxylate. So we need to get rid of this OH, this carboxylic acid group we just formed. So we should get this as our product. So anytime you see NaOH, acid, and then heat, this is the SAD combination. Saponification, acidification, and decarboxylation. What they're used for is just to get rid of ester groups. So we know we have an ester here. So we know we're getting rid of this. So just cut off the ester, basically. And you should be left with whatever's on the right side, and that's what I did. That's why I didn't have to think about it in my mind. We know that SAD is a good way to remove esters. So I know I kind of jumped a few steps. So I'll take you through it step by step of what happens. So first, our base is going to do base catalyzed ester hydrolysis. So what we should be left with is, oh man, messed up. Remember, since we're in base, we don't form our carboxylic acid. We form our carboxylate anion. We form the conjugate base. because we're working in basic conditions. To add that proton in again now, we have to add our acid. So now we form something like this. Okay, so now we form our carboxylic acid. Now we have heat. And so if you remember that one criteria from decarboxylation is that that carboxylic acid has to be beta to your carbonyl. Are these two beta? Well, yeah, if we move one over, we know this is alpha, and then we know this is beta. They have one CH2 group separating them. So let's draw what our decarboxylation should look like. Here I'm just going to rotate around this bond, just so it's easier to get into this conformation. So if you look at it here, there's no reaction that happened. I'm just rotating among single bonds. This is because for decarboxylation to occur, you need a 6-membered transition state. And this is just that right here, 1, 2, 3, 4, 5, 6. So what's going to happen here is this is going to be a loop-de-loop of all the bonds. So this one's going to go back onto here. This one's going to go back onto here. This will go onto here. And this one will go in this imaginary spot between these two. And once we do that, we should end up with so let's just quickly orient ourselves in what happened. This oxygen grabs a proton, so we form an OH. And then what's going to happen here is we form a double bond here, so that's that. We break this off. So essentially this forms a carbon dioxide, so we should have a CO2 just floating around. And the CO2 is formed from whatever's over here. So we get rid of that. So we're left with whatever's not in this circle over here, and that makes sense. But if you look at it, our decarboxylation, it didn't just get rid of the carboxyl group. It also messed up our carbonyl because now we have an enol. So then we have to tautomerize back to our keto form. So that's the last step. And that's how your SAD, your saponification, acidification, and decarboxylation work to just get rid of esters. And you see, if you know these steps, you can just lasso out this ester, and this is the product you're left with. But these are the steps that go into it. So we go this way. So now here's our practice problem. Pause the video, take a few seconds to try it out, and then we'll jump into the solution. Alright, so first step is we use ethoxide. We know ethoxide is a good base. So we have this malonic ester, and we know that the only place we can deprotonate it is at the hydrogen in the center. So we're going to take that off and we're going to form an anion. So here we have our negative charge. So now we created something that can attack. We created a nucleophile. Let's draw out this second step because I don't know what that looks like. So it's 3 carbons and then a bromine on the right side and then a chlorine on the left. So here there's a bit of trickery. There's 2 leaving groups, but which one are we going to attack? Well, we have to think which one's the better leaving group. If I kick off this bromine, I'm going to form Br- in our solution. Oh man, that's bad. Br-. If I kick off this chlorine, I'm going to form Cl-. Which one is more stable? Well, we know that a negative charge is inherently unstable. It just means an excess of electrons. So if I have an atom like this versus an atom like this, the negative charge will be spread over a larger area. Because of that, it's less destabilizing. We know our bromine is larger if we look at our periodic table, so it can stabilize its negative charge better. It's more polarizable. So because of that, it's better to kick off this bromine because we form something that's not as reactive. This is very stable. So we take our lone pair, attack this side, and then kick off this bromine. This is not to say our chlorine is not a good leaving group, it's just preferred that the bromine leaves first. So now you should get 1, 2, 3 with the chlorine dangling off. 1, 2, 3, and then a chlorine right here. And then our Br minus is just floating in solution. That's just gone now. What's our third step? NaOET again. Okay, that's a bit peculiar. So we're going to deprotonate in the same spot again because there's still another hydrogen remaining. Okay, that's a bit weird, but let's just see what they're trying to get at. So we have a anion right here, and then we have this group we just attached, so 3 carbons, 1, 2, 3, and then a chlorine dangling off. So, okay, we have a nucleophile, but then again, we just added an electrophile, because this point right here is an electrophilic carbon. So we can do an intramolecular nucleophilic electrophilic reaction. This carbanion is going to attack this electrophilic carbon and kick off this chlorine. And then what we should get is this. Well, now we have 1, 2, 3 carbons. So 1, 2, 3, and form the square. So this should be your product. Cool. So I hope that makes sense to you guys. Oh, jeez. So let's just review what we went over. We learned that if we have an asymmetrical ketone, we can form either a thermodynamic or kinetic product. We know our thermodynamic is more substituted, more stable. However, it has a higher transition state because it's harder to get in here under all this steric hindrance and abstract that proton. So to favor the thermodynamic, we need to add heat. We learned how that works over here. Then we went into beta-dicarbonyl compounds. They're beta because there's one CH2 group in between. We created enolates from there, and we used that enolate to attack electrophiles. And we learned that when we have these beta-dicarbonyl compounds, we can get rid of the ester in the product by using SAD, saponification, acidification, and decarboxylation. This is the mechanism, sort of, for how that works, and this is just an example problem. Alright, great. So now here's the fun part. Here are the practice problems. So this is the first one. We have a compound here, and we're asking how many possible enolates can be derived. So I want you to draw all the possible ones and then circle the thermodynamic one and then place a square around the kinetic one. Here, just fill in the reactants that somehow get us from reactant to product. This one is tricky, but this one you guys might roll your eyes and think, okay, this is just a really hard problem. It is, but the reason why is because this has shown up on every other exam I've seen. Because in Orgo 1 you guys learned about ring expansion. Here you're sort of contracting the ring, so it's like the complementary reaction. So this one, please think about it and we'll go over it. And then whoever is in my class, please do these 2 problems. This is your homework problem for attendance. So yeah, pause the video, give it a try, and then we can jump into it. Alright, I hope you guys got a chance to try out those problems. So now I'm going to go over the solutions for the first few. So for this product over here, we know that we're going to be creating enolates and any possible ones. So basically we're just going to put a lone pair on any alpha carbon. So if we look at this carbonyl, we know there's an alpha carbon here, an alpha carbon here. So just put a lone pair here, lone pair here. And we know for this carbonyl there's a lone pair here and a lone pair here. So because of this, there's 4 possible enolates you can totally form. So let's draw them out. I'm going to go left to right. So this is the first one if we use our first lone pair. Second one should look like this. Our third one, oh, I didn't finish the oxygen here. The third one should be this lone pair here, so we know it's going to form an alkene on the right side. So we should get this. This is an alkene. And the fourth one, if we look at this lone pair, it's going to form an alkene on the right side. So these are 4 possible enolates. So that wasn't too bad, it's just process of elimination. But now we have to circle the most stable one, the thermodynamic product, and we have to box the kinetic one. So if we remember from our definitions that we just covered over here, our thermodynamic is the most substituted alkene. Our kinetic one is the one that's not. So let's go through it and try and figure it out. So if we look at substitution, we know here it's substituted to 2 alkyl groups. Okay, so this is 2. Here we're substituted to 1, 2, 3. Okay, that's pretty good. Here we're only substituted to 1. That's kind of bad. And here again we're substituted to 2. So the one that has the most substitution is the top right. So this is your thermodynamic. So that one should be a circle. So I'm going to circle this enolate because it's the thermodynamic because it's substituted to 3 alkyl groups. Now it says place a box around the kinetic product. The kinetic is the least substituted alkene. So here we have 2 prime substituted, and here we have 2 prime substituted. This one is on the end, so this one is the kinetic product. And the reason why is it's easier for a base to come in here and abstract a proton from this side because it has the least amount of steric hindrance. So that's why this product forms the fastest. Alright, so I hope you guys were able to get that one. This is the second practice problem. So if we look at it, we know we're going to involve some enolate, but here we have an asymmetrical ketone. So either we can abstract a proton from the left side or the right side. Here we see that the electrophile is added to the right side, so you know we have to go here. Is that the kinetic or the thermodynamic? In this case it would be the kinetic because it's the least substituted alkene we're forming. So we know we have to use a strong base because we're working with a single carbonyl compound, so LDA. If we're forming our kinetic product, we can't use heat. So let's just do negative 78 Celsius. That's bad. Negative 78 Celsius. And so that creates our enolate. And now we have to add an electrophile in. So it's going to be a 3-carbon electrophile. So 1, 2, 3. There's going to be an alkene on one end, and on the other end where it attacked is going to be the bromine. So, pretty simple 2-step box problem. Now this one is the fun one. So, the way you have to think about and approach this is, you know, you're going to have to restructure the ring somehow. And because of that, you have to break it open. So we learned one definite way to break open an alkene, and that's ozonolysis. So we start with this, and we can use oxidative ozonolysis. So let's use H2O2. And that means we're going to get 6 carbons, so 1, 2, 3, 4, 5, 6. And at the end of each carbon, since we're using oxidative ozonolysis, we should get carboxylic acids. Okay, cool. Now let's do Fischer esterification. So let's just add in some ethanol. And for Fischer esterification, it's acid catalyzed. However, here we know that there's two carboxylic acid groups, so we should put a 2 preceding the ethanol because it's 2 molar quantity. And because of that, we should end up with the same thing, just replace these carboxylic acids with esters. So we should get this. 1, 2, 3, 4, 5, 6. Okay, cool. So now we created this compound. Somehow we have to get to this ring conformation. Any ideas? Let's try and think it through. Well, this entire unit, what was it on? It was on enolates. So let's maybe try and create an enolate. Let's use ethoxide to create an enolate at the alpha carbon. So let's see, do I have enough steps to make this work? No. So let's use NaOET, ethoxide, in ethanol. So we know that we're going to deprotonate one of the alpha carbons, so we should get something like this. So let's make a redraw that. So we should get something like this. So now we created a nucleophile in our entire molecule. But now that we have a nucleophile, we know we can attack the molecule itself because there's an electrophile. So if we look at it starting here, there's 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5. And we have a 5-membered ring. So I think the stuff is like starting to add up a bit now, right? So, I can't draw the mechanism on this picture, but what's going to happen is this lone pair is going to come in, attack this electrophilic center. So what we should get is, we know we're going to form a pentagon. The reason why is because there's 5 carbons, 1, 2, 3, 4, 5. And on this first carbon, we're going to have our ester still sticking off. So this is carbon number 1. Now, carbon number 1, 2, 3, 4, 5. So we know if we have this 5th one, we're going to have to do addition elimination. And what we're going to have to kick off is this ethanol group over here. So what we should get on the 5th carbon, 1, 2, 3, 4, 5, is just a carbonyl, because it's going to, your carbon ion is going to come in, attack here. Oh, nice, it works. Push it up. And now this guy's going to come down and kick off this ethanol. So you should be left with this. But we're not there yet. What's the difference between this product and this one? Well, we're lacking this ester group. And if you guys remember, what's the easy way to get rid of any ester? Sad. I'm not going to draw out the reagents, but it's NaOH, acid, and heat. And then we can end up with our product. So it's a pretty 4-step synthesis, but this is like a common tool we use. So let's go over why we did everything. We had to create esters here because we need to be able to get rid of an ester at the final step. So we started off with oxidative ozonolysis to add our carboxylic acids. Then we did Fischer esterification with 2 molar quantity of ethanol and acid. And we created our 6-membered chain with esters sticking off of it. Then when we added base, we created an enolate. The enolate attacks itself, and through addition elimination kicks off this ethanol, so we're left with this. And then we can get rid of this ester by using SAD. So I hope that made some sense. And then for everyone in my class, please do these 2 problems. I'll zoom in if you can't see. This is what it looks like. And just send a picture of it to me by this weekend. So today, what we did was we went over the acidity, basicity of carbonyl groups. We learned about the enolate and how it can do 2 potential reactions. We learned why we need a strong base for enolates. We went over the kinetic and thermodynamic product and how to favor it with heat. We learned about beta-dicarbonyl enolates and SAD. And we did a few practice problems. So I hope this was helpful. If you have any questions, feel free to leave a comment, and stay safe, everyone.